Yeah, so as has been said here, we are mostly working like with drones and like flying robots. So in fact, all of the drones in this presentation are really like independently flying robots. So we don't use any operator, any control station. Everything is computed on board, on onboard PC with onboard sensors. So we are really focused on robotics and on the robotics in the wild. So we have a lot of experiments and deployment in the real world conditions. There are like there is one reason behind that we are maybe the only big drone group worldwide without any flying arena. So we don't have any opportunity of flying indoor or even in netting space somewhere. We always have to go to the real world to do any single experiment, which is really forcing my students and researchers to design the system for real world deployment. So this is where we are strong, and this is also why we were successful in these competitions, as has been mentioned in my CV. I will show you some of the videos from these competitions. I guess you will enjoy it because it was really really tough and real world deployment of robots. Some of the results I'm going to present you are also made together with our spin-off company, Fly for Future. The company is growing a lot. Now it's even bigger than my group. So in my group, I have now 40 people. They hired 10 more people. So now they are 45. So they already, because my wife is CEO of the company. So she was laughing to me that they are already bigger than we are. So I will also present you some of the application-oriented projects that are done at the company. But let's return back to academia and back to, let's say, fundamental research. So this slide is pretty old. I have prepared it for my grant proposal maybe 8 years ago. At that time, we kind of decided with my group that we would like to go to get to the swarms of drones into wild. We were focused on GNSS denied space to be able to fly inside of the forest where you don't have GPS. We wanted to do it scalable, which means without communication, because if you have really large groups of closely flying drones, the communication is still bottleneck. And I was kind of fascinated by the swarming in the nature, like the birds and fish and this kind of stuff. And so we wanted to be kind of motivated by these animals. So that's why we were working on strictly decentralized systems, being able to have large groups, anonymous groups, and fly with in an environment with high density of obstacles. We did a lot of research in this field. The first kind of task we had to solve was relative localization. Imagine that you are flying or operating a lot of robots in the close proximity, and you need to know the states of the robots around you to be able to really flock together. We tried many approaches. We tried RGB cameras, 3D camera, depth cameras, 3D lidars, 2D lidars, a lot of them. Some of them were working better indoors, some others outdoors. But then we found one solution which is kind of useful everywhere. It's based on ultraviolet active markers. So we are using LEDs installed on the drones, on legs of the drones here, as you can see. And all drones are equipped with small cameras with a filter, which is filtering out all the spectrum of the solar radiation except the part of the UV. Oh, sorry, here of the UV, because the advantage of the UV is that it's filtered out by the atmosphere. So you will get really such a black image, and the bright dots is the drone. So in this RGB image, the drone is hidden in front of the cars, and it was not possible to find it any onboard RGB perception, but here you can do it quite easily. And plus, you can get the distance based on the distance calculation between the two bright dots. So let's imagine that these two guys, so you can estimate the distance. Plus, you can also communicate by blinking of these LEDs using different frequencies. So we have designed also some very simple optic communication for swarms of drones. They can't communicate, of course, like long messages, but for example, they can say, like, send around the command, like, now I'm scared by predator, I'm going to escape, or something like that. So this system was quite, as I said, reliable, or it is still. We are still working on it. It's never-ending development, but we have already tens of kind of clients, universities worldwide using this system for swarming in the wild, which was quite good achievement, I would say. Another important part, enabling technology, let's say, we have designed is a system for controlling of a flock of UAVs. We are working on many different projects, as you will see a little bit later. And we wanted to have the system as modular as possible, to be able to use different sensors for flying indoor, outdoor, transition indoor, outdoor, with GPS, without GPS. So our system is capable of integrating many different sensory modalities, even combining them in parallel. It is able to add many different controllers for agile flying, non-linear MPC, linear MPC, PID, of course, controllers, SO3 controllers. There are many controllers, many sensors integrated. It is open source, so feel free to use it. Maybe some of you have heard about it. Some of you are going to attend our school, so we will also learn you how to use it at the school. I will show you at the end the leaflet from the school. We have now more than 1,000 registered active users, so it's also helped us to, since it's open source, it helps us a lot with debugging of the system. We have also designed many hardware platforms based on this software stack. So as I said, there is a lot of groups worldwide using it for their research purposes. Also, there is many companies using it for their R&D and getting to product. Here are some drones examples. Even you can get it in case you would be interested. It's already installed with the system, and you can start playing with it. But let me return back to the research. So we have, this is like, it was published 2022, but we did this experiment, of course, like 2 years before. So let's say 2020, we managed to fly in the wild forest a team of fully autonomous drones without any communication, without GPS, fully decentralized. So, I mean, everything was great, and we got a lot of papers accepted, but for industry, of course, this is not usable at all. They are pretty slow. And also the reliability is not high enough. So, although maybe I will okay. I will show you first a few of our previous projects results, and then I will show you a list of achievements we are working right now. So yeah, so this is, as you can see, the drones are equipped with the UV LEDs, UV cameras. They see each other, and based on this information, they are flocking in the wild. We did also a lot of experiments here in the region. We have been working in Abu Dhabi a lot. So we deployed drones, swarm of drones above the dunes there, in the desert there. Again, this project was focused on GNSS denied deployment. So they are using visual inertial navigation only, VIO. No, they don't communicate. They only see each other by the sensors, and they fly above the desert. Of course, we found out many problems there, mainly in terms of reliability of the visual localization. I will show you some ongoing research at the end of this talk. We did also a lot of night experiments. It was interesting to see or don't see the drones. In fact, these blue LEDs you can see by the sensitive chip in the camera, but as humans we can shift it to the UV part of the spectrum where you will not see the drones. So they are really hidden in the desert and flying, and we hope that they will return back. So again, and here we push the speed. So it was already beginning of our endeavor towards fast forming. We have also a lot of projects on inspection of interiors of historical buildings in Czech Republic. We did a lot of deployments in cathedrals, in castles, many UNESCO heritage buildings even we explored. So you could imagine that we had to design really reliable system to be able to fly in like heritage important places. After my trip here in the country, I will go to UAE, and we are starting a project on inspection of national heritage in Emirates. So they will use results of this project to scan their fortresses in Ajman. So this is just by the way. And let me explain you how this works. So again, the drones are fully autonomous. They are relying on onboard 3D LiDAR. So at the beginning, before flying in the object, we pre-scan the environment by terrestrial 3D scanner. The drones could fly even without the pre-scanned map, but thanks like before, because of the high reliability required, we use this terrestrial scanner. We do like a digital twin of the object, if you like. It is a point cloud for the drone, as well as a 3D mesh for the end user. Then this is done by the end user. So historians select the locations of the camera to make a picture. We get it as an input for our trajectory planner. The drones compute an optimal trajectory to connect all these points to get an optimal trajectory. Then the trajectory is visualized for the client. So these guys can check if it's flying in okay places, you know, if it's not close to some extremely expensive painting or whatever. If it's confirmed, we just bring the drone to the object, press start button, and then everything is done fully autonomously. The 3D LiDAR on the drone localizes the drone in the 3D model, navigates the drone towards the place of making picture. Then the pictures are stored. We can, of course, also see like press scan from the 3D LiDAR as well as from the camera on a screen, but like the highest quality of the data is stored in the drone. So after the flight, we can do two things. Of course, we have the images, videos, and so on, but also we can add the 3D model data obtained by the 3D LiDAR back to the original scan, which was obtained from ground. So imagine if you have there some overlapping, probably you can't see here from the ground, right? Because there was kind of a balcony or whatever, the drone will add this information. We did a comparison with DJI. Of course, we are able to get much better quality of pictures because we could use better camera. We could, and then another important thing is that we can repeatedly visit these same locations, which is difficult to do by a pilot. So it has a lot of usage. We are now also working with industrial applications of this technology. We have project for flying inside of nuclear power plants, not in the reactor hall, but in the machinery hall next to the reactor. So you can imagine the mass of tubes there where the drones need to fly through. And I believe also here in your country, you have a lot of such industrial complexes that require inspection, and it's difficult for operator to fly there by DJI drone. So it could be probably useful here as well. Here you could see also some results of multi-robot deployment in the church. So of course, I a little bit push this application because I'm a multi-robot system guy, right? So what we did was that one drone is carrying a light and the other drone is carrying a camera. So you can get like a better quality of pictures if you are playing with the light. So you can see that the shadows will give you the 3D feeling of the picture, and you will be able to recognize even much more. You can use even some techniques where you can model the illumination based on the results. So there is a lot of different tasks which can be done using fully autonomous teams of drones inside of like for inspection of interiors of buildings. I wanted to ask if you have questions.
The 3D mesh, the resulted 3D meshes, are they going to be post-processed or they're going to be used as they are on the output on?
So both. Like the drone is building its own map for navigation. So you will get immediately a point cloud, which is obtained by the 3D LiDAR. If you need to get mesh, kind of this 3D mesh, like the model with colors and everything for human, you have to do post-processing. And we do it like photogrammetry usually from pictures. No, so they need to tell us which part of the object to scan for photogrammetry, because you need hundreds of pictures from different positions. So, but automatically you will get quite precise 3D model based on the 3D LiDAR. So, for example, in the industry, they don't care about beauty, right? They care about the precise measurement of all the tubes, and everything. So for them, the 3D LiDAR model obtained automatically is enough. For the historians, they always want to have nice 3D models, nice pictures. So depends on the task, yes. But the drone, and this is going to be shown in the next, in fact, slides, the drone is capable of even building the map from scratch. So we can do exploration in completely unknown environment. This I will show you here. So this was the DARPA SAP-T challenge about. So we had to send a team of robots, flying robots and ground robots, into the completely unknown environment. In hostile conditions, dust and everything, and they didn't allow us to enter. So behind the gate, So the drones had to really explore the environment without any help of people, and which means building the 3D map. So we did a lot of deployment in real, this is a mined. Golden mine in close to Denver. We did a lot of other deployment. Maybe I will show you this. This is the most probably interesting part, because this was a deployment in. This is a nuclear power plant, abundant one, and the task was just to fly in without GPS, of course, and to explore the whole environment. They were not interested in the map, but in the positions of artifacts or humans we found there automatically. So the drones or ground robot, they had to report back a very precise 3D position of the objects inside of such a complex industrial environment. So we had to, of course, build a map and precisely localize the drones, and they required precision less than 5 meters in 3D. So imagine after 25 minutes of flight, you have still to keep the precision of the localization around 1 meter, because then you will see something, you have the sensor error, so you have to be extremely precise.
You're not using any sensor fusion to get a better precision?
Yes, of course, but what kind of sensor?
You're using LiDAR.
We have been using 3D LiDAR, which is the most precise.
Yeah.
You can use a vision as well. I will show you later on the results on vision.
I also saw you were using also Aruco markers, or it was.
No. This was without markers. So this was just really completely unknown environment without any help of anything. So you have to do kind of odometry, right? So you have to, because you are building the map and you are localizing in the map. So you can fuse it with VIO, for example, but VIO is not so precise at all as a 3D LiDAR SLAM, I would say. So this is a SLAM. Yeah, but there were problems with 3D LiDARs. Maybe I will. Yeah, I'm not sure if you will see it here, so I will just show you the perspective. So it was really large rooms that had to be explored with small, narrow passages. So the drone had to explore the large area, but then went to small, windows, doors, and there was a time constraint, so we had to fly pretty fast. But this is speed up a little bit the motion. Yeah, so there was this challenge of the using 3D LiDAR, but for maybe I will show you also a little bit of these pictures because I like it. We did some tests, some flying in real cave systems. So really, I like nature, so it was really great to be able to access these natural caves. So we managed to scan a natural system even with some river inside. After like 6 kilometers in the cave, there was a river. So the drone managed to build a map in length of 8 kilometers, fully autonomously. So it was quite impressive, quite precise map, just by SLAM, 3D LiDAR SLAM. But then for the finals, they built a kind of more artificial intelligence in the DARPA Subterranean Challenge, and they were like corridors like this one, which were symmetrical. And the 3D LiDAR, if you can't see the end of the corridor and just you see the walls around, there is not enough features, 3D LiDAR features, to still stay kind of precise in the mapping. So you have drift in that axis, which is like aligned with the axis of the corridor, right? So we kind of didn't crash. The drone was stable, but there was a huge drift in the position error. So that's why we were started to considering two things: how to fly in environment where you have these symmetrical elements, because the same happened to us even in the large historical buildings. Sometimes in the cathedrals you have a symmetrical environment, so you can't measure really one of the axes where you are. So we started to playing with vision as well and fusing the vision. But if you are working with vision, you have also a lot of troubles there, right? So I will, at the end of this talk, I will a little bit speak about that. Yeah, so these are the pictures from the finals. It was at the end great experience. For the finals, we had to fly in a combination of caves, artificial mines, metro station. We didn't know what will be inside, so it was quite like a lot of fun. So we were happy to be at the end second in this huge competition in the virtual challenge at least. And we also managed to publish a lot. So there is a lot of publications. So if you are working on 3D SLAM, I recommend you this one. It is in fact all teams participating in DARPA SAPTI. So you will see the famous names working on 3D SLAMs. Decided to work a paper together on showing really the state of the art. So this is kind of interesting paper to read. Okay, more questions regarding the DARPA SAPTI or flying in the subterranean? If not, I will come closer to to the region. So this was the MBZRC competition that has been mentioned. So in fact, it kind of opened a lot of opportunities even for us here in the region, not only UAE, but also in Oman. This is back like to 2017, so I will skip this. It's already too old, and maybe I'll show you a little bit of the results from 2020, which is still, it's already also becoming old, but let's let's see. So the challenge there was quite nice. They organized some firefighting challenge where we had to fully autonomously like put some water into the fire. We had to build walls by drones, and also capture some unauthorized flying target. This is an overview of the competition. I will go fast through it. It is competition only, so it was a little bit artificial, of course. We had to catch this ball, this yellow ball. We were not able to damage the flying drone because, of course, they couldn't continue with the competition. Then we built the wall by fully autonomous robots. They didn't tell us the location of the piles with bricks. We had to localize them, grasp it autonomously, bring it to the location of the wall. Also, the location of the wall was not known. We had to scan it, find it. Then the firefighting was also interesting. It was a combination of many different tasks. There was a facade fire, there was an inside fire, there was some fire next to the building. We had to also combine it with ground robot. So it was extremely challenging and complex task. So we were proud to win this challenge entirely, combining all these sub-challenges. But also it gave us a lot of publications. This is just a selection. Before I had two slides, but of course nobody will read it now. So I just, in case you would be interested in any of these publications, let me know, or just visit our webpage. But what I want to tell you that there was a lot of industrial outcome out of these challenges. It was intended by the organizers, in fact. So they motivated the challenge by real problems. So one of them is like firefighting in, this is kind of Burj Khalifa, kind of, but probably, or for sure, you have the same tall buildings here. And you can imagine this is a problem. So we were even contacted by a European company working on firefighting drones. So we designed some prototypes based on the competition results, which is equipped with a 3D camera and thermal camera to localize the fire and to shoot such cartridges to the fire to diminish the fire. We designed full-scale drone. So this drone is really flying robot. It is able to localize the fire. So inside of the fire, or inside of the house, there is a fire. The drone is able to shoot repeatedly, to shoot that cartridges inside, and the fire is done. This was one of the testing we did.
Is it counted or depend on the fire?
Excuse me, I didn't get the.
Is it going to shoot countable number of packages, or
So
you can see the fire that was gone, so he will stop?
No. I mean, it was intended to shoot there everything it has.
So it will shoot
everything, because I mean, you don't care. You don't want to save this €5 cartridges in case you are, so of course, it's always shooting there everything. The amount is counted the way that it should help in normal flat fire, so up to 100 square meters. So it's quite a lot, to say true. So 100 square meters, it should diminish. Now it's on the market. It's already like some European firefighters are testing it in the real conditions. So I'm not allowed to show you the real pictures. Maybe in a couple of months I will be. So I hope it will be successful at the end. There is another project which is also kind of it's using a lot of from the competition. Mainly we integrated the 3D LiDAR detection into the drone. So it's a drone hunter. So it's a drone, and you are here working also on a similar project. So I don't have to introduce you the problem and the and the task. I will rather show you the results. So this is a product which is already on the market. It was like designed with cooperation of my company together with company Eagle.one, which is owned by some investor from Czech Republic. So they designed that platform, which is kind of really like a heavy duty platform. It's pretty heavy, carbon, everything. Like it's intended to survive impact to the target as well, and it's equipped with this releasing net to be able to catch the flying target. Before, at the beginning of the project, we were shooting a net the same way as the cartridge, in fact. The problem was that in case of high speed and wind, the light net was like too much, affected by the wind. So it was in fact good only for slow targets. But they want to push the agility of the drones. So now with this releasing net, we have non-linear model predictive control on board. We are capable of predicting the motion of the target, and we are able to really do an aggressive maneuvers and repeated maneuvers, because the net is, once you shoot the net, you are done, right? But here we have the net attached and we can do repeated trials. Do you have any question regarding these projects?
Yes. So you're still talking about something that's only controlled with the LiDAR.
I didn't mention it, but this is a fusion of LiDAR and cameras.
Okay.
So, in fact, the 3D LiDAR is fused with GPS for navigation and localization. So, in case there is like GPS denied part of the environment or the precision of GPS is not sufficient, the drone can fuse 3D LiDAR. It is, in fact, building a similar map as in case of the historical buildings. Then, for detection of the target, the 3D LiDAR is again the main sensor. So it can, in fact, detect that there is something not attached to the ground. So if there will be, I don't know, like a small, like you can imagine like the light, the bulb of the light, it's always attached to the ground. So these objects are not considered to be drone. But if it's flying and released from the drone, then there is a neural network which is kind of confirming that it's drone, not a bird. And all these sensors are fused together to get the relative position of the target and even to do some prediction of the motion to be on the position of the target in future, right? You are not kind of visual servoing, but you are like the planner. In visual servoing, usually you have for example, the fire, right? So there is a target, and you really try to go to the position of the target. But here, it's a moving target. So we are not interested in the current position, but in the future position. So this model predictive control is using in the objective function the model of motion of the target. So it is kind of trying to align with the trajectory of the target and get there in the future.
What do you use for prediction? Predict the
I will get to it later. So far we use mainly the information from the 3D LiDAR and from the camera. So in fact, we are just using many relative localization information, which is like in the time changing. So we try to estimate the velocity out of the position, which is of course noisy. So now we want to go, and I will show you a little bit later. We want to estimate the state of the drone directly. We know that, for example, if it's inclined like that, it's like flying this direction, right? So this information we try to fuse. Even we try to detect the frequency of props. Because imagine that if you want to do an aggressive maneuver, you have to start rotating these props faster, But this is ongoing like research. I will show you a little bit of it later on. So it's not in the industrial product yet. This is purely on the like position estimation. And also we get position estimation from the external positioning system. So imagine that there is some system doing the alarm. Here is some guy flying, take off from the recharging station, go to the position. So we have some preliminary information about the trajectory of the target. In most of the cases, DJI and so on, it's just following waypoints, so it's straight line and easy to estimate, and it's easy to catch. But if it's a experienced pilot trying to escape, it's another game, yes, which is funny, or kind of, because it's good like game, theory. Okay, so I'm going to the second part, or last, maybe third of my presentation, I would say. So maybe now the guys who has already seen my presentation in Oman wake up. These are the challenges we identified, like in these last few years. As I have mentioned, mainly the agility and the speed of the swarm. It was too slow, and we want to really be agile. So we now are working on nonlinear control, on fast perception, both like the ego navigation, which means if you are flying extremely fast through forest, everything is blurry, and even the 3D LiDAR is blurry. So how to navigate fast, localize fast, and also how to do the relative localization of the target if everything is extremely fast. So these are the open challenges we are now heading. How to increase the reliability of GNSS denied localization. This has been already a little bit discussed. The degraded environment without features. So it can be above the desert where there are not enough visual features, flat sand, right? It can be in the corridor. And the problem that proper sensor equipment depends on the environment. If we will be flying above the desert, we can't use 3D LiDAR because there are no objects around. If we are flying in long, wide corridor, vision will not help you because you don't have visual features. So how to combine multiple sensory modalities? And also, which is also now extremely important, is long-range missions. Once we are flying fast, we have to build like really huge maps, and now it's also intended because or not tanks, but because of that conflict in Ukraine, now everybody wants to fly without GPS, long missions, high altitude. So you have to build really big global maps. And also scalability in the real world. This is interesting. How to design the perception which will be able to detect hundreds of drones. I want to get in really huge swarms as the birds are doing. And also we are now going to aspects of heterogeneous systems with different dynamics. So this is the ongoing work in my group, let's say. So the first one is fast for swarming in plain GNSS denied environments, which was in fact motivated by our work in UAE, flying above the desert. So there are some partners even from institute in Abu Dhabi. They work together with us. So the problem was what to do in case if some of the drones are not able to see enough visual features. And we kind of raised the question, can the other drones help? The answer was surprisingly yes. Or I mean, probably this will not surprise you much. So imagine in these experiments, there are some UAVs without any velocity information. So you know that for stabilizing the drone, you have to measure the velocity. You have to have optic flow at least, or VIO, or whatever. But if you are above flat desert or even grass and you have the down-looking camera, you may lose this. There are not enough visual features. So some of these drones, and at the end, only one drone is able to do to use like VIO. So purposely we switched off VIO in all of the drones. They are not using GPS. The only sensors they use is the relative localization, that UV DAR with UV LEDs. So they know about states of the others. And they are flying pretty fast now already. So we showed that you can use the swarm to help you with localization in poor environment. But what to do if none of the UAV is without velocity measurement? So my student came to me and said, okay, I will try this. And I said, it's nonsense, no? If you don't have any measurement of the planet, in fact, you are not attached to the rest of the world, it will be unstable, clearly, right? He said, okay, let me try it. You have a question? No, no. Let me try it. And surprisingly, he got a very good results from, I don't know why the video is stopping. Yes, now they are flying. So here, none of the UAV is using, in fact, any sensor information. So they don't use GPS, they don't use optic flow, they don't use VIO. They just see the other drones around. And the motion is, in fact, drift of IMU. And why it's relatively stable. I will show you maybe later on. So here, that yellow guy is without the velocity information. Oh, it's still stopping. Yeah, so, and it's not connected to the others. Could you see it? Crash immediately. After 3 seconds, the drone crashed, you know. If it has no sensor information, it will crash immediately. And these are connected together. And why it is? Imagine that you have IMU installed on many drones. Each of the IMU is with huge drift. We don't use the professional IMUs of 3 kilograms weight and extremely cost price on the small drones. So the IMU is with the drift and mainly the accelerometers, but this drift is random. So if you have many kind of distributed IMUs with random drift, with random noise, and you are combining them together because you see the others. So altogether, it's not stable, but it is few orders more stable than a single drone. So then the guy even tested, if you are going to tens of drones, they will really be hovering, you know, and maybe start drifting after a long time, you know, because they are kind of accumulating the error. And it is not the same as of course, you can say, okay, so let's put three IMU on the drone. Would this help? Yes, it would. And many companies is doing that, you know. But if you are distributed in the space, the IMUs, it is like, you know, I'm here attached. Maybe I have a barometer right here and here because barometer is there. So for me, it's difficult to, you know, rotate that because they are kind of more fixed as a team than if you put everything on a single spot. So then even it will be less stable. So this was an interesting achievement, how the drones, swarm of drones, how it can help. Usually like having more robots will bring problems and less reliability, right? But we showed that the drones in the team could work and help. So it was interesting.
So I have a question here. So we did something similar with the UWV sensors with ground robots with relative localization, and we showed that you have relative position stability. So what would be the difference here? It's just you're using
there is a one big difference with UGVs and UAVs. The UGV is stable. So if it's stable system, UAVs is unstable, right? So you need to have in the control feedback some, in fact, velocity measurement. Otherwise, it's unstable. It's different from planes. If you will fly fixed wing, it's stable system. So if in case you will be without any sensory measurement, it will fly, not crash. But the drone, no, it will crash immediately in 2 seconds.
I think the attitude is stabilizing. I think you're talking about position stability, right?
Yes.
Yes, but the position stability is the issue here. But the attitude itself is stabilizing. You can hover if you have relatively stable sensor feedback.
Yes,
Optical flow, you can do it.
Exactly. But here you don't have it.
So instead of using, for example, optical flow, you're using the relative information.
Exactly.
Yeah.
To the others. So
what you can do is to have ground robot as an anchor. So this ground robot will kind of attach you to the ground because you know that this robot is with 0 velocity because it's staying on the ground, right? Or any beacon. And once you are connected to the beacon, you're stable. But here everything is flying in the air. So this is the difference. That here you don't have really the anchor. So we also call it, maybe I didn't write it here, no, but we call it flying without anchor. You know, because you don't have any information about the warp. In fact, you are then like, you know, your coordinate system is then not attached to the real warp. So you could think that I'm stable, but in fact you are not. You know, so in your coordinate frame you are stable, but the coordinate frame is doing that. Exactly. Yes, exactly. And if you put more coordinate frames together by any kind of linkage, like your UVB would work the same. So we can also use UVB. The only difference is that here we have quite precise bearing information, not so precise distance. With UVB, you will have very precise distance information, but not like heading at all. You have to combine many of them and communicate.
So I think we did another experiment with drones where we have, an altimeter, like a 1D LiDAR to measure height, so you can stabilize height. And then you have UWB sensors. Of course, you don't have a global frame coordinate, but
you can be stable.
Exactly.
Yeah,
exactly.
So here you're using just visual relative information.
Exactly. Like to say true, of course, we know about UVB technology. We are also able to fuse it with that vision-based relative localization. So we are kind of still, in my opinion, it's not reliable enough. If you have many drones, many UVBs, it's overlapping, and there is noise and problems, you know. So that's why we don't use it regularly in large swarms yet, but it's promising. So combination of vision and UVB is probably the best way.
You studied how Ingenuity, the drone that is on Mars with Curiosity, is working with that reckoning that they're doing. I think that
so they were using optic flow or VIO. Simply.
Yeah, IMO and altimeters.
Exactly.
We approximately the same thing with that reckoning. No?
Yeah, but they were using vision.
They were using vision like VIO. I'm not sure if it was optic flow or VIO, but that's why they did extremely short hops only. You know, because with VIO or with vision, with optic flow, you can be precise for short flight. If you want to fly a long flight, the VIO is drifting a lot. And in Mars, also you don't have objects around like nice buildings, you know, everything is the same like desert.
I think in January it crashed.
Yes, at the end it did. At the end it crashed, and this was because of exactly this. There was not enough visual features. I met the guys from the team a week ago in Japan, so they exactly explained that exactly. Yes. So in fact, this was our paper there at ICRAD the last week, which is towards the scalability issue I have mentioned. So now we are able to localize just few drones around by this UVB, vision, whatever, but I want to go to hundreds. So here we try to estimate, not particular. So imagine that you have here four drones. It's kind of easy to detect all of them, you know. But if you have here this experiment with here, you know, this is the input. So we used 100 drones in a single field of view from camera. And with onboard processor detecting position of 100 drones that are overlapping. No way. So we try to train the neural network in the way that it will give us the density of the swarm. So then, because like imagine that you are the bird in the swarm of birds in the flock, you will see just the neighbors, few of them. Somebody said that 6, 7. In case of starlings, I don't know, but maybe. And then probably they use an information about the whole group, but they don't use information about a single entity. You know, it's impossible. They are flying with 30,000 animals in that flock. So probably they kind of are able to sense the density of the flock around. And we really tried, and it is working quite well. You can get in real time the density information of the swarm around, and then use the swarm controller just to use this information. Few local neighbors for collision avoidance, and the rest to keep the cohesion of the swarm. So this is kind of bio-inspired swarming work we are doing right now. And this is another interesting. I have a team of people now working on extremely agile flying, because I want to go to such an agile flying and swarming. So this is a non-linear MPC on board of a small drone in real-world conditions. So it was first time somebody was flying with onboard sensor and onboard perception in the wild, kind of. So you may know Davide Scaramuza's work inside in the laboratory. Ask him if he can take it out immediately. No, because you have to solve different challenges. So now we are working on this agile flying. It's super cool to see the super fast drones. You know, this was here. This is only 25 meters per second. Then there will be even 35 and 3.5 G, and still it looks already impressive. You know, and now we managed to go to 6 G. So you know this. F-35 fighters are already working or flying with 5 to 6 G maximum. So you are really reaching the limit with such a small drone. And this is another interesting work, in my opinion, or I like it personally, because now we are able to detect even the props. You know, so there is a drone, and the other drone is equipped with event-based cameras. Again, Davide Scaramuza introduced the event-based camera to the robotic community. You have heard about it probably. So it is so fast and getting you the event so fast that this drone is flying relatively to us like full speed. So in fact, it is 0.1% speed of the video. So it's extremely slowed down. So you can see the props frequency. And now we are trying to get from this information the inclination of the drone, how it's tilted, and also the frequency to be able to estimate the full state of the drone. So not only the velocity and acceleration, but even derivation of acceleration. Because if you want to accelerate, you need to start rotating more, right? So it could change everything, maybe, for the swarming and also for drone hunting. Okay, so I'm going to the last few slides. This is just to show you that we are also working with marine robotics because, yeah, similar as you here, I want also to explore different areas. So we have been building autonomous boat. Now we are working on we have done it already. It was published. Autonomous landing on the boat in harsh conditions, such a wavy sea. We have designed a system for deploying of buoys with measurement units. The drone is able to capture it, catch it from the water autonomously. Yeah, these are some pictures. I hope it will be working. Yes, of the drone flying, doing takeoff from the boat. Here is recharge. So the boat is equipped with solar panels, so it can recharge. You could see some cables going to the landing platform. We are doing also, this is also autonomous boat. It's towing this sensor unit. The drone is helping with state estimation of the boat and autonomously landing. So it was also published in Robotics and Autonomous Letters, in case you would be interested in. We did also a lot of on inspections in real world conditions. So this is high voltage inspection. I will not continue with this. You can imagine there will be drones doing the inspection of high voltage. Probably it is also, it would be applicable here in this region a lot. There is an opportunity to do some experiments with you in case you would like. So we got some funding from European Union for remote kind of experiments with our partners. So just send me email. We have money to pay our platforms and our engineers to prepare an experiment for you. So you can really do some experiment with us. This April, we did maybe 5 experiments with different universities worldwide. Some guys came to Prague, some were remote, and it was a lot of successful experiments. So we will be having papers together. So it's kind of good opportunity in case you would like to go to the wild. Yes, this I will skip. And the last thing, you know, some of you about the summer school. We have still few. Yeah, this is a wrong slide. There is already no early build registration. It's we are going already to reach the limit of the school. Now we have 200 participants approved, and the capacity is 230. So we have like 30 last slots available. So in case you would like to attend the school, go to Prague, enjoy the summer there, and meet us and meet my students, let me know, and there is a possibility to register. So this was everything from my side. So thank you for the attention. I hope it was not too long, but I wanted to show you everything, guys, you know, as always.
Yeah, thank you very much.
Pretty much impressive work. That's pretty much nice. So we'll have room for discussion. You know, I just have a question. I have many questions, but let me start with one question. So now, one of the slides that you've mentioned that where you deploy the drone within a forest, and you mentioned that, okay, you can make papers, but it's very slow. It doesn't go to production. How do you manage to bridge the gap between what we do in academia and the business?
Okay. So you mean in general? Yeah. So, like, to say true, we are able to put to the business maybe 5% of the research results. So, for example, this swarming, you know, almost nobody is interested in industry. You know, I got a lot of questions. Why to fly without GPS? You know, why to fly without communication? Why to fly in such teams? You know, and now there is the crisis in Ukraine, and everybody is coming. And can you please design some multi-robot system without GPS, without communication? You know, even our army came to me, you know, and I told them, come on, guys, I told you already 2 years ago, you know, you didn't understand, you know. So I just want to say, you know, so we have many more approaches. Most of them will be never used. Sometimes we are just playing, you know, we are researchers, you know, how it is. So for example, this imitating of birds. Is it useful? Probably no, you know, but maybe, you know, imagine that, again, probably defense, you know, imagine that there is agile, small bees flying towards you, you know, you have no chance, you know. So still, of course, industry is few steps behind us as researchers, but in this drone industry, everything is so fast, right? So, I mean, I remember it was like, I don't know, 5 years ago. There was I saw some on ICRA conference results of the flapping wings drones, you know. So it was pretty new. And then after 8 months, one could buy it as a toy for $20. You know, I said like, come on, you know. So it's unbelievable, you know. The same happened with VTOLs, right? Yeah. I remember it is like not maybe 6 years ago. No, it's not so long time ago. I remember the groups, they were trying to manage this transition, you know, from this, for example, from this taking off and then go to the plane mode, you know. And now there is many companies doing it, you know. So it's amazing how fast it is in the drone industry. Yes. And also, like, of course, companies are taking our guys to make it this faster, and also we are pushing it. So, but still, of course, I mean, there is a lot of like these event-based cameras. It's so promising, you know. We are now using it for relative object detection, but also for navigation in the forest. Because, as I said, imagine that you are using normal camera, which is sensitive to illumination. If you are flying inside of a forest or indoor, whatever, and you don't have enough light there, you have long exposure time, you are flying fast, everything is extremely blurry, you can't use it. With event camera, easy. But you know, the price is now 4,000 euros still. You know, so imagine that you'll tell the industry, you should put 3 or 4 of these small cameras and you will pay just 4,000 for each, you know. And then you need a good processor, you know, computer. So, but once we will be using it more, the chip will go down. Yeah. So the 3D lidars, no? Are you aware of this? I forgot the name of the new 3D lidar, which is, maybe I will get it later on. So so far we are using before Velodyne, right? Now we have been using Osters. The price of the best Oster, 10,000, something like around 10,000 euro. And now there is a new company, Livox, with this new 3D lidar. We have tested it. It is much better than the Oster. $700.
Yeah, we got one.
Longer range, better precision. We tried some SLAM. It worked immediately. You know,
yeah.
700.
I couldn't believe when I saw it the first time. Livox, $700.
I thought it will be shit, you know, but it is much more reliable. It is all the parameters are the same as the 10,000 Oster or better. So all the parameters and also the reliability. So we are struggling a lot with Osters. Sometimes there is missing packet from some reason. Sometimes there are some parts are not available. You know, it's not so reliable. With Livox, of course, we are shortly working with it, but without any single problems. So the same, right? Probably with the event cameras, there will be some. I mean, the technology is easy of the event cameras. There is the same chip as on normal cameras. The only difficult part is how to read the events, like how to read it. So it's kind of almost software based. You know? So of course I know it was extremely expensive for the company, so they have to get the money back. So it's expensive, I know. But there will be some other companies copying it, and it will go down to the normal price of cameras. And yeah, then we have to be prepared.
Right. Any questions? For sure there are many. Yes.
For the drone hunters, how does this identify the target as unauthorized to be in the premise?
This is a good question. We are not able, of course. I mean, if there is like, usually it's intended to protect non-flying zones. So we expect that everything which is flying and doesn't look like a bird, it's our target, you know. Yeah. In that product, they have, of course, confirmation. So there is a human in the loop, which is pressing the button. Yes, you can start. Yes, this is the target I want to catch. You know, so you expect that this guy is able somehow to do that, but if not, I mean, of course, you can get the good guy as well.
And then does it change it? Does it chase it outside the parameter of the non-flying zone?
No, no, of course not. I mean, we know that there is fans like normal, right? Normal technology. So we still fuse GPS. So like the GPS, even if it's not so precise, you have error 10 meters, you are still okay with this geofence, right? So geofence is still there.
So regarding the target detection, so you have heavily used 3D lidars in your work, and still they are not at the price of what normal cameras. Much more expensive.
But not so much now, right? 700. But anyway.
Okay, Elon Musk will not agree with that.
Yeah, I know. But ask all the Volkswagen and Mercedes groups, and they will not agree with Elon.
Yeah, I understand. But I'm not going to compare human capabilities to robots, but we don't need LiDAR in order to estimate relative positions, right? And if you want to miniaturize the drones, instead of having heavy drones to carry the heavy LiDAR, not only the cost, but the payload.
Yes.
And it's compromised, every gram compromises, especially multi-rotors. So if you are only allowed to use a single camera, maybe two, they are cheap, would you be able to detect and localize? Because detection itself, relatively with the coming AI technology, is possible, but the localization is more difficult without using a LiDAR.
So yes, of course, yes. Let me respond to your like, which I like this that humans are also using vision only, right? So I agree with you. I'm also thinking like that. But imagine that you would be kind of deployed as a human in a cave system, and you have to explore the caves, going back there, trying to find the person, and then you have to report the position in precision in 3D in less than 1 meter after 30 minutes of walking in the caves. No chance at all. No. Even if you would be extremely well in this task, for example, I would be lost completely. I would even remember the topology. Yes. Not exactly, not after 30 minutes, you are lost. I mean, of course, you can say, I hope north is there. Or I hope the entrance is there. But like saying, I have these 3D coordinates, come on. So that's why the 3D LiDARs, probably they are still better for this precise localization. Otherwise, like the reliability, maybe it will be better at the end with the cameras. Once of course, our brain is still much better than the best processors on board, right? But exactly. So, but once more, probably there will be there will be some computers soon with the same computational capacity. So I believe that vision is the way. Small drones, definitely, but the precision and the reliability is not there yet. So we use it mainly in all industrial projects. And you could see it. The swarming was with vision, because we know that for some short experiment it will work. And in case one of the drone will be lost, come on, we will restart the experiment. You know how it is, right? But for industry, the 3D LiDAR reliability is really somewhere else than the vision yet.
Any other questions?
Can we get the slides, a copy of them?
Yeah, sure, definitely. Yeah, I have it somewhere online. If not, I will put it there. So
Okay.
So sure.
We will email you so you can show us. Send an email.
Yeah, so ask me, or if you can distribute the link,
Sure.
I will just send you a link to. I will put it online somewhere, so it's maybe. Sure, I can do it even like after the talk. I can use your very fast network. I see. So my data wouldn't do it because it is quite. So I will put there a PDF as well, because this is 2 gigabytes with videos, right?
Alberto, for GPS denied navigation, based on your experience, what now could be the best approaches or things that could be probably more investigated to improve the GPS navigation capabilities?
Well, maybe I will not answer directly to your question, but I will tell you what I see like challenges right now, which are still open and not solved. I have a little bit mentioned that it's this long range outdoor navigation or localization. If you are flying inside and you have the objects around, the 3D LiDAR will work after 1 hour of flight. So you will be still localized very precisely. But if you are flying outdoor, far from obstacles, relying only on vision, it's difficult to really keep the long range flight, the precision, and also how to store the huge amount of information you are gathering during the mission, right? So there are some techniques that allow even like large scale mapping, but still it's not reliable. And the second important challenge is the how to deal with featureless degraded parts of the environment. So I have mentioned the symmetry. It's everywhere, but it's not only, of course, it's everywhere in human-made kind of environment, like corridors, very bad, you know, wide walls. But it is even in the nature, for the desert, water surface. Wow, this is the most challenging. Probably you know, and that was the MBZRSC challenge, the last one, right? I helped to design it, but at the end it was too much military for me, so we didn't participate. But exactly, it was GNSS denied above water surface. Come on, you don't have anything, you know. I mean, even pilots back before the GPS was founded, kind of they were lost, right? So they use some visual markers and they hope that there will be the island. It's stars. You can use stars as the sailors before, you know. So this is still open. These are the open challenges. Yes. Exactly. Probably no, right? But maybe with the help of Swarm, Swarm will help you with everything. Yeah. Exactly. Yeah. Exactly. Stones, or what? Astronomy. Yeah, exactly. Stars, as I said, like this. Yeah. And another interesting is the sensor fusion. So if you imagine that you don't have perfect conditions, you have fog, you have dust. So radars are working pretty well. They are not so precise yet as 3D LiDARs. So, but the fusion of radars, 3D LiDARs, vision, thermal vision, multispectral cameras for navigation as well. So it's a lot of interesting approaches. You know, even some radars that were able to penetrate like walls, you know, and see something behind. So this could also help you in case you don't have, if you are in just corridor. I don't know, you know. I just.
I heard that there are some birds which can detect some underlying features, underground features.
Exactly. Yeah. I wanted to say. Exactly.
So if there are subtypes of sensors that can detect such underground features.
And the birds are somehow using the more precisely than just us, right? We just use the one direction information, which is not enough, but they are somehow able to see more.
They are even affected by the solar exposure.
Yeah.
And the KP index get high, they get lost.
I see. Yeah, exactly. Yeah. So yeah, it's funny. I like this bio inspiration a lot because I like nature, you know, and I also like to do scuba diving, and now I found that there are groups. I knew it before already that they are studying the fish, you know, schools and like schooling and that. But now they are using robotic sensors. They are putting them on the fish. And what's funny, I found it recently we are now writing a project together because I would like to study it more. Imagine the fish school of salmons. They are placing a sensor on the fish to be able to retrieve the full 3D position, in fact, and acceleration. So it's equipped with IMU and everything, the same sensor as we have. In fact, they don't know it, but it is. And they put it also on the main, how it's called, fin, or that. Yeah. And so what they can kind of observe how this, for example, a stress is propagated. So imagine that there is a predator or a source of feed or something which is being propagated through that group, and they see that probably they are able to observe the vibrations from that main actuator. In fact, this is their actuator. So they can react before they will change even the orientation. So they don't observe the position or the velocity or the acceleration. They observe the derivative of the acceleration, because once it's starting to do that, it will accelerate in the next moment, right? That's why they can be so agile. So let's put it on drones. This is a challenge, So this I like. But this is probably really basic research. I don't believe that companies will use it soon. But who cares?
Another question. Okay, thank you, Martin. We enjoyed the presentation. Thank you very much. Thank you.
Next one.